Welcome. In this comprehensive exploration, we will examine two fundamental concepts that form the backbone of statistical analysis and decision making: probability and relative frequency. Probability is the mathematical measure of how likely an event is to occur. It quantifies uncertainty and ranges from 0, meaning impossible, to 1, meaning absolutely certain. Relative frequency, also known as experimental probability, is an estimate of probability based on observed data from actual experiments or real-world observations. It provides a practical way to estimate probabilities when theoretical calculations are difficult or impossible. Understanding both probability and relative frequency is crucial for making informed decisions in numerous real-world scenarios. From weather forecasting and medical research to quality control and risk assessment, these concepts help us quantify uncertainty and make data-driven decisions. Throughout this comprehensive exploration, we will examine the theoretical foundations, practical applications, and real-world examples that demonstrate the power and importance of probability and relative frequency in statistical analysis and decision-making. Theoretical probability is fundamentally different from experimental approaches. It relies on mathematical principles and makes a crucial assumption that all possible outcomes are equally likely to occur. The theoretical probability formula is straightforward. We divide the number of favorable outcomes by the total number of possible outcomes. This gives us a precise mathematical value. Consider a fair six-sided die. Since the die is fair, each of the six faces has an equal chance of landing face up. The theoretical probability of rolling any specific number, say a 3, is one favorable outcome divided by 6 total possible outcomes. A coin flip provides another clear example. With only 2 possible outcomes, heads or tails, and assuming the coin is fair, each outcome has a theoretical probability of 1/2 or 50%. Theoretical probability has several important characteristics. It is based purely on mathematical analysis rather than experimental data. It assumes perfect conditions and requires that all outcomes be equally likely. This approach provides exact probability values that remain constant regardless of actual trial results. Understanding theoretical probability provides the mathematical foundation for probability theory. It serves as the benchmark against which we can compare experimental results and helps us make predictions in idealized scenarios. Complement of an event is a fundamental concept in probability theory that helps us understand the relationship between what happens and what doesn't happen in any given situation. By definition, the complement of an event includes all possible outcomes that are not part of the original event. Think of it as everything else that could happen instead. Let's visualize this concept. Here we have our sample space, which contains all possible outcomes. Event A represents some specific outcomes we're interested in. The complement of event A, denoted as A prime, consists of all the remaining area in the sample space. It represents every outcome that is not part of event A. The mathematical relationship is beautifully simple. The probability of the complement equals 1 minus the probability of the original event. This makes perfect sense because all probabilities must sum to 1. Let's apply this concept to a practical example that demonstrates how complements work in real-world situations. Consider weather forecasting. If the probability of rain tomorrow is 0.3, what is the probability of no rain? Since no rain is the complement of rain, we can calculate it easily. Using our complement formula, the probability of no rain equals 1 minus 0.3, which gives us 0.7. This means there's a 70% chance of no rain. The key insight is that complementary events are mutually exclusive and exhaustive. They cannot happen simultaneously, and together they account for all possible outcomes. This fundamental relationship makes probability calculations much more manageable. Weather forecasting provides an excellent real-world example of how meteorologists use relative frequency to make predictions about future weather conditions. Meteorologists collect historical weather data over many years. This data includes information about sunny days, rainy days, cloudy days, and other weather conditions for specific locations and time periods. Let's examine a concrete example. Suppose meteorologists analyzed weather data for the month of April over the past 20 years in a specific city. They recorded 600 total days of data. From this historical data, they found that 360 days were sunny, 150 days were cloudy, and 90 days were rainy. Now they can calculate the relative frequency for each weather condition. To calculate relative frequency, we divide the number of occurrences by the total number of observations. For sunny days, 360 divided by 600 equals 0.6 or 60%. Similarly, for cloudy days, 150 divided by 600 equals 0.25 or 25%. And for rainy days, 90 divided by 600 equals 0.15 or 15%. Now, meteorologists can use these relative frequencies to make predictions. When forecasting for next April, they can say there's a 60% probability of sunny weather, 25% for cloudy conditions, and 15% for rain on any given day. This approach allows meteorologists to provide data-driven forecasts based on historical patterns. The more historical data they have, the more reliable their relative frequency estimates become, leading to more accurate weather predictions. In manufacturing environments, relative frequency serves as a critical tool for quality control. Companies use this statistical method to monitor defect rates and maintain product quality standards. Consider a production line manufacturing electronic components. As products move along the conveyor belt, quality inspectors examine each item to identify any defects. In this batch of 20 products, quality inspectors identify 4 defective items marked in red, while 16 products meet quality standards and are marked in green. The quality control system tracks these numbers systematically. The counter displays the total count of products inspected and categorizes them by quality status. Using the relative frequency formula, we calculate the defect rate by dividing the number of defective items by the total number of items inspected. 4 defective items out of 20 total gives us a defect rate of 20%. This calculated defect rate is then compared against established quality standards. If the company's target is to maintain defect rates below 5%, the current 20% rate clearly exceeds acceptable limits and triggers corrective action. This data-driven approach enables manufacturers to identify quality issues quickly, implement corrective measures, and continuously monitor improvement. By tracking relative frequency over time, companies can detect trends, prevent quality degradation, and ensure consistent product standards. In medical research, relative frequency serves as a powerful tool for estimating the probability of disease occurrence. Researchers analyze observed case data to understand disease patterns and inform public health decisions. Consider a seasonal flu study, where researchers monitor 10,000 patients throughout flu season. Their goal is to estimate the probability of flu infection using observed case data. During the study period, researchers observe and record each case of flu infection. Out of the 10,000 patients monitored, 1,500 develop flu symptoms and test positive. The researchers compile their observed data: 10,000 total patients, 1,500 flu cases, and 8,500 who remained healthy throughout the study period. Using the relative frequency formula, researchers calculate the probability of flu infection. The number of flu cases divided by total patients gives us 1,500 divided by 10,000, which equals 0.15, or 15%. This 15% probability estimate has significant public health applications. It helps with risk assessment to identify high-risk populations, resource planning to allocate medical resources effectively, prevention strategies to target intervention programs, and policy decisions to inform vaccination campaigns. The key insight is that relative frequency transforms raw medical data into actionable probability estimates, enabling evidence-based healthcare decisions that can save lives and improve public health outcomes. Relative frequency is a powerful tool for detecting bias in dice and coins. By comparing observed frequencies to theoretical probabilities, we can determine if an object is fair or biased. Consider a dice experiment where we roll a die 100 times. For a fair die, each face should appear approximately 16.67% of the time, or about 17 times out of 100 rolls. However, if our die is biased toward face 6, we might observe face 6 appearing 30% of the time, significantly higher than the expected 16.67%. This large deviation suggests the die is not fair. For coin experiments, a fair coin should show heads and tails each 50% of the time. Small deviations are normal due to random variation. However, if a coin shows heads 70% of the time and tails only 30% of the time, this 20% deviation from the expected 50-50 split strongly indicates the coin is biased toward heads. The key to detecting bias is comparing observed relative frequencies to theoretical probabilities. While small deviations are normal, large and consistent deviations indicate bias. More trials provide more reliable detection of bias in dice and coins. Sample size is a critical factor that determines the reliability of relative frequency estimates. When we use relative frequency to estimate probability, the number of observations or trials directly impacts how accurate our estimate will be. The fundamental principle is straightforward. Smaller sample sizes can lead to inaccurate probability estimates, while larger sample sizes provide more reliable results. This relationship is crucial for anyone working with statistical data. Let's demonstrate this with a coin flip example. Consider flipping a fair coin, where the true probability of getting heads is exactly 50%. With a small sample of only 10 coin flips, we might observe 7 heads and 3 tails. This gives us a relative frequency of 70% for heads, which significantly overestimates the true probability. However, with a much larger sample of 100 coin flips, we might observe 52 heads and 48 tails. This gives us a relative frequency of 52%, which is much closer to the true probability of 50%. This demonstrates why sample size matters so much. The larger sample provides a more accurate estimate because random fluctuations have less impact when averaged over many observations. This principle applies to all statistical applications, from quality control to medical research. The key takeaway is that sufficient sample size is essential for reliable probability estimates. Before drawing conclusions from relative frequency data, always consider whether you have collected enough observations to ensure your estimates accurately reflect the true underlying probability. When working with relative frequency data, we must carefully consider potential biases that can significantly impact our results and lead to incorrect conclusions. Bias refers to systematic errors that consistently skew our data away from the true values we're trying to measure. Unlike random errors, biases create predictable distortions in our results. The two most common types of bias in relative frequency analysis are sampling bias and measurement error. Sampling bias occurs when our sample doesn't accurately represent the entire population we're studying. Measurement error involves systematic mistakes in how we collect or record our data. These errors can consistently push our results in one direction, creating false patterns in our relative frequency calculations. Consider a survey about public policy support. A biased sample that only surveys city residents might show 85% support, while a representative sample covering all regions equally reveals the true support is only 52%. To identify and mitigate bias, we should use random sampling methods, ensure our samples are diverse and representative, standardize our measurement procedures, cross-validate with multiple data sources, and carefully document potential sources of bias. Remember, unbiased data leads to accurate relative frequency estimates and reliable conclusions. Always question whether your data collection methods might introduce systematic errors that could mislead your analysis. Confidence intervals provide a powerful way to express the uncertainty inherent in probability estimates derived from relative frequency. Rather than giving a single point estimate, they offer a range of plausible values. A confidence interval provides a range of values within which the true probability is likely to lie, with a specified level of confidence. This accounts for the natural variability we see in sample data. Consider a scenario where we estimate a probability to be 0.65 based on our sample data. A point estimate gives us just this single value, but it doesn't tell us how confident we should be in this estimate. A confidence interval, however, provides a range. For example, a 95% confidence interval might be from 0.58 to 0.72. This tells us we can be 95% confident that the true probability lies somewhere within this range. Different confidence levels produce intervals of different widths. A 90% confidence interval is narrower, while a 99% confidence interval is wider. Higher confidence requires a wider interval to capture the true value. Sample size significantly affects confidence interval width. Smaller samples produce wider intervals, indicating greater uncertainty. Larger samples yield narrower intervals, providing more precise estimates of the true probability. Confidence intervals serve as a crucial tool for quantifying uncertainty in probability estimates. They enhance the reliability of relative frequency estimates by providing a range rather than a single point, helping decision makers understand the precision of their estimates and make more informed choices under uncertainty. Relative frequency is experiencing unprecedented growth in risk assessment applications. Organizations across multiple sectors are leveraging historical data patterns to make more informed decisions about potential risks and their management strategies. Three primary sectors are leading this transformation. In finance, institutions analyze historical market data and credit patterns to assess lending risks and market volatility. Insurance companies use decades of claims data to calculate accurate premiums and predict future claim frequencies. Public health organizations utilize relative frequency to model disease outbreaks, conduct epidemiological research, and develop evidence-based health policies. By examining historical health data patterns, they can better predict and prepare for future health challenges. The risk assessment process follows a systematic approach. Organizations collect extensive historical data, calculate relative frequencies of various risk events, and use these patterns to predict future probabilities and develop mitigation strategies. This data-driven approach provides significant advantages. Organizations can quantify previously subjective risks, make more accurate predictions based on actual historical patterns, and develop targeted strategies that address the most probable risk scenarios. As organizations continue to generate more data and develop sophisticated analytical capabilities, the role of relative frequency in risk assessment will only continue to expand, making it an essential tool for modern risk management across all sectors. Enhanced data collection methods are revolutionizing how we gather information for probability analysis. Modern technologies provide larger, more representative data sets that significantly improve the accuracy of relative frequency estimates. Traditional data collection methods were often limited by manual processes, small sample sizes, and time constraints. Modern approaches leverage technology to gather vastly more data points, creating comprehensive data sets that better represent the true population. Several key technologies are driving these improvements in data collection. Let's examine the most impactful methods that are transforming how we gather data for probability analysis. Internet of Things sensors provide continuous real-time data collection across various environments. Digital platforms enable systematic data gathering through web-based systems. Mobile applications allow widespread user participation, dramatically expanding sample sizes and geographic coverage. These enhanced data collection methods directly impact the accuracy of relative frequency estimates. As we collect more representative data, our probability calculations become increasingly reliable and precise. This chart demonstrates how accuracy improves as dataset size increases. Small datasets may achieve only 60% accuracy, while big data approaches can reach over 95% accuracy in relative frequency estimates. Let's examine specific examples of how enhanced data collection methods are being applied in real-world scenarios to improve probability estimates and decision-making processes. Smart city traffic systems use thousands of sensors to collect real-time data, improving accident probability predictions by 40%. Wearable health devices continuously monitor millions of users, providing accurate health risk assessments. Financial markets utilize high-frequency trading data for precise market movement probability calculations. Enhanced data collection methods provide three critical benefits for probability analysis: significantly larger sample sizes, more representative data sets that better reflect true populations, and improved accuracy in relative frequency estimates. Throughout our exploration, we have seen how probability and relative frequency serve as fundamental analytical tools across numerous industries and disciplines. These mathematical concepts provide the foundation for data-driven decision-making in our modern world. In meteorology, weather forecasting relies heavily on relative frequency analysis of historical weather patterns. Meteorologists examine decades of data to calculate the probability of specific weather conditions occurring under similar atmospheric circumstances. Manufacturing industries utilize relative frequency to maintain quality control standards. By tracking defect rates over time, companies can identify trends, predict potential quality issues, and implement preventive measures before problems escalate. Healthcare professionals depend on probability calculations derived from relative frequency data to assess disease risks, evaluate treatment effectiveness, and make evidence-based clinical decisions that directly impact patient outcomes. Financial institutions and insurance companies extensively use relative frequency analysis to assess risk levels, determine premium rates, and make investment decisions based on historical market behavior and actuarial data. Despite their diverse applications, all these fields share a fundamental approach. They convert observed data patterns into actionable insights. This transformation from raw data to informed decision-making represents the true power of probability and relative frequency analysis. The universality of these concepts demonstrates their fundamental importance in our data-driven society. From predicting tomorrow's weather to assessing medical treatments, probability and relative frequency provide the mathematical framework that enables evidence-based decision-making across virtually every field of human endeavor. As we conclude our exploration of probability and relative frequency, let's review the essential takeaways that will guide your understanding and application of these fundamental concepts. First and most importantly, understand the distinction between probability and relative frequency. Probability measures the theoretical likelihood of events occurring, while relative frequency provides practical estimates based on observed data from real experiments and trials. Second, the law of large numbers serves as the crucial bridge connecting theoretical probability with experimental results. This fundamental principle tells us that as we increase the number of trials, our relative frequency estimates become increasingly accurate and approach the true theoretical probability. Third, sample size plays a critical role in the accuracy of your probability estimates. Small samples can lead to misleading results, while larger samples provide more reliable and trustworthy estimates. Always consider whether your sample size is adequate for drawing meaningful conclusions. Fourth, always remain vigilant about potential biases in your data collection and analysis. Sampling bias, measurement errors, and other systematic issues can significantly distort your probability estimates. Critical evaluation of your data sources and methods is essential for accurate results. Finally, mastering these concepts empowers you to analyze and interpret data effectively in any field. Whether you're evaluating medical research, assessing business risks, or making personal decisions, understanding probability and relative frequency gives you the tools to think critically and make informed choices based on solid statistical principles. These key takeaways form the foundation of statistical thinking. Remember them as you encounter probability and data analysis in your studies, career, and daily life. They will serve as your guide to making sense of uncertainty and drawing meaningful insights from data. Thank you for joining us on this comprehensive journey through probability and relative frequency. We hope this educational content has provided you with a solid foundation in these fundamental statistical concepts. Throughout this series, we explored the theoretical foundations of probability, discovered how relative frequency provides practical estimates from real data, and examined the crucial role of sample size in statistical accuracy. We also covered real-world applications spanning weather forecasting, medical research, quality control, and emerging trends in machine learning and risk assessment. If this content helped deepen your understanding of probability and statistics, please consider liking this video and subscribing to our channel for more educational mathematics content. Mathematics is a powerful tool for understanding our world, and probability theory opens doors to making informed decisions under uncertainty. Keep exploring, keep learning, and remember that every expert was once a beginner.